Hello, welcome to part 3 of chapter 9. In this last part of the chapter, we will talk about angular momentum. Angular momentum is the tendency of a rotating object to keep rotating. An object with lots of angular momentum is harder to stop rotating. We can get some insight into angular momentum by comparing linear momentum, which we've already studied in this chapter, with angular momentum. So recall earlier in this chapter how we derived the expression for linear momentum. We started with Newton's second law, F equals ma. We replaced the acceleration with the change in velocity, delta v, over delta t. So we substituted this expression in, and we got force is equal to mass times delta v over delta t. Then we did a little trick, and we took the mass and we moved it up next to the velocity. And we called this product, mass times velocity, momentum. And so we use the letter P for momentum. So Newton's second law in linear form, meaning for objects that travel in a straight line, looks like force is equal to the change in momentum divided by time. So let's now redo this for the rotational form of Newton's law, which we learned about in a previous chapter. Instead of F equals ma, remember we replace force with torque, and we replace mass with rotational inertia I, and we replace the acceleration, linear acceleration A, with alpha, the angular acceleration. So remember, alpha, angular acceleration, is the change in omega, or rotational velocity, divided by the time. So we get the same equation, we just replace v with omega, and we replace A with alpha, and of course we replace F with torque, and we replace M with I. So proceeding as we did over here, we now have net torque is equal to I times delta omega over delta t. And now we're gonna do the same trick. We're gonna take this I and bring it up into the numerator and group it with omega. So net torque is the change in I omega over the time, delta t. So this product, I times omega, is called angular momentum, and we give it the letter L for angular momentum. So this, you can see these two equations are, pretty much the same. We just replace force with torque, and we replace P with L. And then our definition, of course, we replace M with I and V with omega. So the idea here is that over here we saw that force causes a change in linear momentum. Over here we see that torque causes a change in angular momentum. And angular momentum, L, which is equal to I omega, is our subject for this last part of the video. So once again, just to make sure this is clear, let's compare regular or linear momentum with angular momentum. So linear momentum, P, is equal to mass times velocity. So what we do with angular momentum is we replace the P with the letter L. That's what we use for angular momentum. Mass, or inertia, is replaced with rotational inertia, I. And V, velocity, is replaced with omega, which is the angular velocity. So angular momentum is the product of rotational inertia and how fast it's spinning, which is its angular velocity. Just, for a couple of conceptual examples, a car wheel that's spinning very fast as you're driving down the road has a relatively large angular momentum. It has a lot of mass, therefore its rotational inertia is large, and it's probably spinning very fast. It has a large omega as well. A bicycle wheel obviously is going to have less angular momentum than the car wheel. It has less mass, so it has less I, and it's probably not going as fast, so it has a smaller omega as well. And then something like a CD or a DVD that's spinning would have a relatively small angular momentum because of its very small mass and therefore small rotational inertia. So in the rest of this lecture, what we're going to do is work through a bunch of examples And I'm also going to show you a bunch of demonstrations, some of which are kind of interesting. Angular momentum, I think, is one of the more fascinating topics of introductory physics, as hopefully you'll get to see in this video. So let's just start with some examples first. So we saw a problem like this earlier in the course where we determined the torque and so forth of the child pushing on this floating giant granite sphere. So it's an amusement park exhibit, has a large solid granite sphere with a mass of 25,000 kilograms and a radius of 0.8 meters. It floats on a frictionless layer of thin water underneath here, so we can treat this as a frictionless problem. The child pushes the sphere so that it rotates at 0.2 radians per second. So in this problem, we're told what the angular velocity of the sphere is. It's rotating at 0.2 radians per second. What is the sphere's angular momentum? So in order to figure out angular momentum, remember L is equal to I omega. So we have to know what I is. I is the rotational inertia of this sphere. And this is something, again, where we have to look up in a table in for a lot of these problems. So if we go back to the table from the chapter on rotational dynamics, I believe it was chapter 7, we'll find that for a solid sphere, the rotational inertia is given by 2/5 mr squared. So again, this is something that you don't remember or memorize, and you don't figure it out from scratch. You just look it up in a table. Then we just plug in our numbers. 2/5 is, of course, 0.4. The mass, 25,000. R is the radius, which is 0.8, and remember to square it. And this gives us 6,400 kilogram meters squared. So that's our rotational inertia. The angular momentum then is this rotational inertia I, 6,400, times omega, which was given to us as 0.2. So 6,400 times 0.2 is 1,280, and that is our angular momentum. And you can see the units here. We're using regular kilogram meter second units, so we can end up with kilograms meters squared per second. In some of the problems that we'll encounter, we have to deal with a compact object, which, in physics, we call that a particle. That's just an object that's relatively small and compact and has all its mass located in one region here. So if we have an object like this particle here of mass m and it's rotating around in a circle, we're going to need to figure out the angular momentum of this rotating particle. Now, earlier in the course, we saw that the rotational inertia I for a rotating compact object was equal to mr squared. So again, we did this back in, I believe it was chapter 7. The other thing we learned about an object going around in a circle is that omega is equal to the velocity of the object in meters per second divided by the radius. So multiplying these both together, we get this expression here, mRV. Notice that one of the r's canceled there. Now we can rewrite this. We can put the r in front, and we have mass times velocity. Well, mass times velocity is the momentum of this particle, the linear momentum. So interestingly, for this case here, the angular momentum L is equal to the linear momentum P multiplied by the radius r. The other useful result, again, by using this relationship between omega and v, is that L is equal to mr squared omega. So there may be instances in this chapter, either in the problems we're going to do today in this lecture, or perhaps in the homework, where you may have to use this result. So here's an example where we can use that result. We've got a 100-gram ball, twirls around on a string. This is our overhead view. The string has a length of 1.2 meters, and the speed of the ball is 2 meters per second. What is the ball's angular momentum? So using our result from the last slide, L is equal to RP, and remember P is equal to mv, mass times velocity. So we can just plug in our numbers. R is 1.2 meters, the mass is 0.1 kilograms, and the velocity is 2 meters per second. And multiplying these three numbers together gives us an angular momentum L equal to 0.24. We saw in the part 2 of this chapter's lecture, one of the important conservation laws of this universe that we live in, and it was the conservation of momentum. Well, here we have one that's equally as important. It's the conservation of angular momentum. And the proof of it is not that difficult at all, but I'm just going to state the law here, and we're going to use this this property or this law of conservation of angular momentum to solve problems and also to show some interesting phenomena in demonstrations. So the law of conservation of angular momentum says that if there is no external net torque present, a rotating object or system of rotating objects must have a constant angular momentum. The angular momentum is conserved, meaning it cannot change. So in other words, at writing all this, a lot of words, right? But writing it as an equation is very simple. L final equals L initial for a system. This just means that the final angular momentum is equal to the initial angular momentum. It does not change, and that's what we mean by conservation of angular momentum. So perhaps the most classic example of the conservation of angular momentum is the figure skater that does a spin. And what he or she does is basically gets their body turning with arms out, and oftentimes one of the legs is also placed outward. Now remember, the axis of rotation is a vertical line going right through her body like this. And so she's going to rotate about that axis. So what she's doing here is she's establishing some amount of angular momentum L, and we can call this L initial. And by placing her arms outward and her leg outward from her body, from the axis of rotation, she is making her rotational inertia large. Remember, we saw this back in chapter 7. When we move mass away from the center of a rotating object, we increase the rotational inertia. So she starts out with a large amount of rotational inertia and a relatively small amount of angular velocity. But then what she does is she tucks her arms in really tight to her body, and notice she brings her legs in tight too. So now all of her mass is located directly along the axis of rotation here. Therefore, she has reduced her rotational inertia to a very small number, but her angular momentum, L final, has to stay the same because of conservation of angular momentum. In other words, LF is the same as Li. So if this is small, that means her angular velocity has to increase in order to conserve angular momentum. So as she tucks in her arms and legs, she starts to spin faster. So you'll enjoy seeing this video clip following here of a figure skater, and watch carefully how she starts with her arms out and then tucks them in and spins faster. There are a lot of interesting demonstrations to show how angular momentum works, and you'll get a chance to see some of these. I'll be doing some of the demonstrations here at home, and I'll also have a couple of clips of other instructors doing various demonstrations. And I wish I could be in the classroom with you live, because these are kind of fun to do, and sometimes I have the students interact and do these demonstrations as well. But at least you'll get a chance to see how some of these work. So enjoy the demos. Hi there, guys. This is your instructor, Jerry Pinter, and I'm here in my lab to demonstrate the conservation of angular momentum. So we learned in the lecture that angular momentum, L, is equal to I, which is rotational inertia, times omega, which is angular velocity. So when we say that angular momentum is conserved, we mean that it stays the same. So what that means is the product of I and omega has to be constant. So if one of these terms, for example, if I gets larger, then omega will have to get smaller, and vice versa. If I gets smaller, then omega will get larger. So what I'm going to do in this experiment is I'm going to start with a large value of rotational inertia. And remember, rotational inertia has to do with where the mass is located compared to the axis of rotation. So if I'm in this chair and I can swivel around like this, if I hold these weights, these are 10-pound weights, if I hold them out far like this, I have a large angular, a large rotational inertia. So I'm going to start my motion with these weights out like this, and I'm going to keep I large and omega. So what we're going to start with I large and a relatively small omega. What I'm going to do then is bring the weights in closer to my body, which will reduce I. But in order for L to be conserved, that means my angular velocity will have to increase. So let's go ahead and do the experiment here. I'm going to put my feet up as well, kind of to get them out of the way so I don't kick anything, and that'll also help me reduce my rotational inertia. All right, so here we go. So we're starting with a relatively slow speed, and I have a large rotational inertia. Now let's bring the weights in. Fast, and then I can bring them back out, and I slow back down, bring them in, and I go fast again. So during this experiment, we're conserving angular momentum, even though we're changing the individual parameters that affect it. And I'm getting kind of dizzy, so I'm going to have to stop now. Hello again. I'm going to show you another demonstration of conservation of angular momentum. In more advanced physics classes, we learn that angular momentum is actually a vector, and it points along the axis of rotation. So when I have this bike wheel here turning, the angular momentum points along the axis. Now, if I turn the wheel upside down like this while it's turning, so in other words, I start like this, and then I flip it upside down like this, well, now the angular momentum vector has completely switched directions. It's pointing in the opposite direction. So the question is, what happens if I'm on this swivel chair and I turn this wheel upside down? Well, the angular momentum has obviously changed, right? It hasn't maybe changed in magnitude, but it certainly has changed in direction. And we know that angular momentum is conserved, which means it's not allowed to change within the system. So what happens here is when the wheel's angular momentum changes, reverses direction, it has to transfer that change in angular momentum to me in the chair and the whole system in order to conserve angular momentum. So let's watch what happens here as I'll get the wheel spinning here. I'm gonna get my feet up again off of the floor. So here we go. I'm gonna start with the chair not rotating. I'm gonna start at rest. Okay, here we go. So you can see me, it started turning me. And if I go the other way, I stop. So let's try it one more time. In fact, let's start this direction, and then I'll flip it the other way. And you can see now I turn in the opposite direction. And this stops me, and then this starts me turning again. So in this demonstration, the total angular momentum of the wheel and me did not change, okay? But what happened when the wheel's angular momentum reversed direction, obviously I had to assume some angular momentum to compensate for the angular momentum change of the wheel so that the whole system had no change. So in this video clip up here, we see what an instructor has done is taken a bike tire like the one I used. Obviously, if you tried to hang it on a string like this without it spinning, it would just fall down and would not balance at all. But what happens here is when it's spinning, you're generating angular momentum, and the angular momentum has a certain amount of tendency to stay in a certain position. And so without getting into too many of the details here, what happens is gravity, which tries to turn this thing down so it falls, it actually causes the thing to precess and rotate in a circle. So this is an action, this is called a gyroscopic action or gyroscopic effect here. And the other one here is shown down here, but this is the little toy gyroscope. When it's not spinning, and if you try to balance it on the little stand here or on the ground, it just falls down, of course. It's not balanced. But when you spin it real fast, you can set it up on that stand, and you'll see that it actually stays balanced on there without falling. Instead, it just precesses around. So kind of fun. So let's now turn to some example problems to use angular momentum to solve. So in this one, we have a small mass m is attached to the end of a string that revolves in a circle on a frictionless tabletop. So you can see that here's a little mass, it's connected to a string, and the mass is going to go around and around here. We'll assume that the tabletop is very slippery, so there's no friction. The other end of the string passes through a hole in the table. And so you can see what's happening here. The string goes through this hole and then goes down here, and the string can be pulled here, which effectively shortens the radius of the circle here that the mass is going to travel around. So initially, the mass revolves with the speed VI equals 2.4 meters per second in a circle of radius 0.8 meters. The string is then pulled slowly through the hole so that the radius is reduced to R2 is 0.48 meters. What is the speed V2 of the mass now? So we can kind of predict here before we even do any math what's going to happen. When this mass is initially rotating around here, it has angular momentum. When the string is pulled, the radius is reduced. So now it's going in a smaller circle. And so what happens here is its value of its rotational inertia actually decreases here, which means it has to go faster to conserve angular momentum. So let's see though how we can solve this. We know that the conservation of angular momentum says that the final angular momentum, LF, is equal to the initial angular momentum. So remember that for a mass or a particle on a string like this, we can use L, angular momentum, is equal to R times P. So let's replace L here with RP. So we have RF PF equals RI PI. And then of course P is regular momentum, is mass times velocity. So replace this P with mvf and this PI with mvi. Then what we're going to do is solve for V final. That's what we're asked to do, is figure out how fast is this thing turning after we shorten the string. So V final you can see is right here. So we have to divide by all this stuff in front of it, the R final times M. So we get V final is Ri times mass times initial velocity divided by R final times mass. And notice the masses cancel. All right, we can cancel those out. So our answer, V final, is equal to the initial radius, which is 0.8, times the initial velocity, which is 2.4, divided by the final radius, which is 0.48. And that comes out to be 4 meters per second. So we can see that, sure enough, the velocity has increased from its initial speed of 2.4 meters per second to 4 meters per second. We can do a sort of a simulation demonstration of this same problem in the following video. Instead of doing this on a table, I'm actually going to do it in the air so that we can reduce friction completely. So we're going to do a little demonstration of conservation of angular momentum. I have a tennis ball with a string on it, and I've got the string passing through a little piece of tubing here. And so what I can do is get some angular momentum started with the tennis ball rotating around my head, and then I'm going to shorten the string by pulling the string through the tubing. And we can watch what happens as the rotational inertia decreases when the string gets shorter, because the mass now is closer to the pivot or axis of rotation. By decreasing rotational inertia, the angular velocity omega has to increase. So here we go. All right, so now I'm going to start pulling the string shorter. You can see the ball speeding up. This next example is sort of reminiscent of the one in the previous section where we had a truck driving along and we dropped a big heavy boulder on the back of the truck, and we saw that the truck slowed down in order to conserve momentum. So this is sort of the rotational equivalent of that problem. What we've got is a rotating disc, or like turntable or platform here. It's turning, and we drop a bar, a mass on top of it. All right, and so afterwards this thing turns like this. So we've got a long thin rod is dropped onto a spinning disc is shown. What is the final angular velocity of the disc? So we're told the disc has a mass of 60 and a radius of 2, and its initial omega is 6 radians per second. Also, the bar has a length of 4 meters, and it has a mass of 20 kilograms. So that's all the information we know, and that's all we need to know. So what we're going to do here is we're going to use conservation of angular momentum. The final F is equal to the initial F. The final L, angular momentum final, is equal to initial angular momentum. What we have to do, though, to figure out angular momentum, remember angular momentum is equal to I times omega. So we need to find the rotational inertia for the disk and for the rod. So again, this is something that we don't, memorize or have in our head or figure out even. We just look it up in a table. So going back to the table on rotational inertia for various shapes from chapter 7, for a rod, notice that this rod, after it's dropped on there, it's going to rotate around the center of the rod because it's dropped straight across onto the axis or the pivot of this disc. So we're going to use this particular shape here. Notice the rotation is right through the center of it. So I is equal to 1/12 ml squared, and you can plug in the mass of the rod and the length of the rod and come up with the value of 26.7. For the rotating disc down here, that's the solid cylindrical disc, which is again is in the table. Its rotational inertia I is given by 1/2 mr squared, and you can plug in the mass 60 and the radius is 2, and you'll come up with a rotational inertia of 120. So we're going to use these results when we plug in our numbers later. So back to our conservation of angular momentum. We have the total, this is the final picture over here. This is our final angular momentum. Notice these two objects now are combined. They turn as one object. So we can add the rotational inertias together, I disk plus I rod. And the final omega is how fast this thing is turning now. That's what we're trying to solve for. The initial position over here, there's a little trick here. We're talking about angular momentum. So this bar is not rotating, all right? It's going to drop and, plop down on top of this disc. But before it lands, there is no angular momentum to this disc. I'm sorry, for this this rod here. It's not turning. So the only thing that has angular momentum is the turning disc here. So that's why we have I of the disc times omega I, which is its initial angular velocity, which is given. So we can solve now for omega final by dividing by the total rotational inertia here, and we get this expression here. And then we can fill in all our numbers. Remember, we found I for the rod, and we found I for the disc here, and we also know the initial omega for the disc was 6. So plugging in all these numbers, we end up with 4.9 radians per second. So let's think about what that means. The disc was originally spinning at 6 radians per second. After we drop this rod onto it, it slows down to 4.9 radians per second. Why is that? Well, it has to conserve angular momentum. But what's happened here is the disc has gained mass now. So it has more rotational inertia. So therefore, it has to slow down in order to keep the same amount of angular momentum that it had over here. You'll see a video demonstration of this. I didn't have any fancy equipment here, so I found a dinner plate that spins, and the demonstration works quite well, and you'll be able to see this in action. This is a demonstration of the conservation of angular momentum that we just saw in the last problem. So I've got a dinner plate here, and interestingly, this dinner plate is kind of defective. It has a rounded bottom, which allows it to spin like a turntable. So I can give this plate initial angular momentum like this, and then we can add this bar here. It's a board of wood. Just like in the problem, we can drop this on top of the plate. And what this is going to do is add rotational inertia to the system. So in order for angular momentum to be conserved, the angular velocity of the system is going to have to slow down when we increase its rotational inertia. So let's go ahead and do our experiment here. One more time. So a lot of angular velocity, and now a much lower angular velocity. Here's another example of using conservation of angular momentum. This time we're going to apply it to an Olympic diver. So this diver has a height of 1.9 meters and a mass of 75 kilograms. He leaves the platform in a straight position like this with an initial angular speed of 5 radians per second. So when he jumps off the high dive here, he gives himself a little bit of rotation by pushing off with his legs. So his body is turning like this. What he does then during the dive is he tucks his arms and legs. Now, why does he do that? Well, when he tucks his arms and legs, this is just like the figure skater when she tucks her arms and legs together as well. This is going to increase his speed of rotation in order to conserve angular momentum. He's basically making his rotational inertia smaller by making his body more compact. Therefore, he has to speed up and will turn faster. So we're going to estimate his final angular speed. So we're not going to do this, precisely or exact, but we can model this, the diver, as some simple shapes. So we're going to assume in this initial position here, the diver has the shape of just a uniform rod. And we can look up the rotational inertia of a rod. It's 1/12 ml squared. And we know the length of the rod is the height of the diver, which is 1.9 meters. For this one over here, it's a little more tricky, but basically the diver has tucked his arms and legs so that he's almost shaped like a sphere, right? He's become like a ball. So we'll use a solid sphere to model this over here, and it'll give us, remember, we're just trying to estimate the angular speed here. So this will give us a decent answer. So we're going to use, for a solid sphere, again, referring back to the table, the rotational inertia is 2/5 mr squared, and r was given as 0.5 meters. So once again, conservation of angular momentum says that L final equals L initial. Remember, L is equal to I omega, so we have I final, omega final equals I initial, omega initial. And we're going to solve for omega final. That's what we want to get. So omega final is equal to I initial, omega initial divided by I final. And we can plug in all these results that we got up here for the I's. And finally, we can put in our numbers. We know all the numbers here. We know the mass of the diver, the length of the diver. We know the radius of the diver when he's tucked into a ball. And we end up with 15 radians per second. So you can kind of see what's happened here is he's got an initial speed of 5 radians per second, and his final speed, angular velocity that is 15 radians per second. So he's speeding up his rotation rate by quite a bit in this problem. So here's our last problem of the chapter. In this one, we've got a 20-kilogram child running at 3 meters per second, jumps onto the edge of a stationary merry-go-round that has a mass of 100 kilograms and a radius of 1.5 meters. So you can kind of see the picture here. The kid is running in a straight line, she's going to jump right on the edge here. And you can kind of guess what's going to happen. This thing's going to start to turn, right? So what is the angular velocity of the merry-go-round after the child jumps on? And how long does it take the merry-go-round to make a complete revolution? So to solve this problem, we're going to model the merry-go-round as a solid disk. Remember, for a solid disk, I equals 1/2 mr squared. That's the rotational inertia. Now, what do we do with the child? Well, the child is running. This is a top view. This is the merry-go-round over here. And here is the child with a mass of 20. She's running towards the edge of the merry-go-round and jumps right on the edge here. So this child actually, when she reaches the merry-go-round right here, she has angular velocity, all right? And her angular velocity, remember, this is like a particle at a distance r from the center. When she gets right here and jumps on, she's basically moving to the left, and she's a distance r from the center. So we're going to use that, the child is providing all of the initial angular momentum. And then once she jumps on, of course, the child and the merry-go-round are both rotating together because she's holding on to the edge. And so we're going to try to find this final omega here. So conservation of angular momentum says that the final angular momentum of the child plus the final angular momentum of the ride, the disk here, is equal to the initial angular momentum of the child plus the initial angular momentum of the ride. So let's work backwards here. So the ride, initial position is here. The ride is not turning yet, so it has no angular momentum. So we got a 0 there. For the child, we just calculated that up here. The angular momentum is r times p. Remember, for a particle that ends up going in a circle, and p is equal to mv. So we have rmv, and this is the velocity of the child. On the left side, what we can do here is we can calculate these separately. Remember, this is in the final position here. So what we've got are two objects. We've got a child and we've got the ride, and they're both rotating together. So they have the same omega. This omega is the same as that omega there. So for the child, remember, this is a particle out here on the end of a distance r. So we can use mr squared. Okay, this was the we actually did this back in chapter 7 to find the rotational inertia of a particle. And then for the ride, that's the solid disk we set up here, that's equal to 1/2 mr squared. So we've got everything included now. What we're going to solve for is this omega here. So we can factor out the omega. Notice both terms have omega. And we get all of this stuff inside parentheses here. To solve for omega, we just divide by all this stuff in parentheses. So here's our omega. It's Rm v child over mr squared plus 1/2 mr squared. And we know all these numbers. We know the radius of the ride, the mass of the child, the initial velocity of the child, and that's pretty much everything. Oh, and this big M here is the mass of the ride, which is 100 kilograms. The little m is for the child. So plugging in all the numbers, we end up with the omega, which is the angular velocity of this whole system here, is 0.57 radians per second. The problem also asked, how long does it take once the child jumps on? How long does it take for this thing to turn one complete revolution? Well, we're talking about the period there, the period of revolution. And if you remember back from rotational dynamics and rotational kinematics, the period of a revolving object is equal to 2 pi divided by omega. So we take 2 pi and divide by this number here, and that gives us 11 seconds. So that is chapter 9. I will see you again in chapter 10. Goodbye.